Welcome to today's webinar hosted by the Institute of Navigation titled Results on GNSS Spoofing Mitigation Using Multiple Receivers, published in the spring 2022 issue of Navigation. Navigation, the journal of the Institute of Navigation, is now open access. You can read, download, cite, and share this and many other papers, and it can be accessed at navi.ion.org. Today's webinar is being presented by one of the paper's authors, Dr. Gustav Hendeby. Dr. Hendeby received his PhD degree in automatic control in 2008 from Linköping University in Linköping, Sweden. He is an associate professor and docent in the Division of Automatic Control, Department of Electrical Engineering at Linköping University. His main research interests are stochastic signal processing and sensor fusion with applications to nonlinear problems, target tracking, and simultaneous localization and mapping. He is the author of several published articles and conference papers in this area. Following the presentation, we'll take questions. To ask a question, you can click on the Q&A box in your viewer. So thank you for being here, and now we'll turn it over to Gustav.
Thank you very much for that introduction. So I would like to start to thank my co-authors of this paper, Niklas Stenberg, Erik Axel, and Jonny Rantakoko, all with the Swedish Defense Research Agency, FOI. They have been really helpful in this writing here. And actually, this paper is the result of a master's thesis that Niklas did back in 2019 that we have since been working on. And as the title says, what we're doing is spoofing mitigation. So that will be interesting here to see what I have to say about that. And one of the key aspects here is that we managed to do the mitigation, and we managed to actually validate results on real live data. So first, why is this interesting at all? Well, GNSS receivers and GPS has been growing in importance since a couple of years, or quite many years by now. And we use it not only for positioning, so we have them as positioning in autonomous systems or whatever, but we also use them for time synchronization in critical systems in our infrastructure. So it's a key thing to have working. And it's also really easy to jam GPS or GNSS. It's been seen in several instances, and also to spoof. As I try to illustrate with these pictures down here, I mean, we could have a boat in the sea getting proper position information from the satellites, and then someone introduces a spoofer, and all of a sudden I think that I'm on land, which is of course not a proper position for the boat. And this has been observed in, for example, the Black Sea. And that shows that this is a topic that is of high interest at the moment. Okay. So a short outline of our method. It starts with the observation that the signals that come from proper satellites behave differently when you move the GPS receiver compared to a signal from a spoofer. We will have a time difference that is different when we have two different locations for the receiver if we come from a proper satellite constellation, whereas the change in behavior with the spoofer is not that. So that is what we're going to use. And the idea is that the receivers, they track several signals from the satellites, both the authentic one and the spoofed one. So that's one of our assumptions here. And then we take double differences of the distance and or the carrier phase from the different satellites, and then that way try to reveal which signals that we have that are spoofed. And by removing these spoofed signals, we can then determine a proper position and velocity time estimate, and that's the mitigation that we're aiming for. So my plan for today is to first give you the background, the theoretical background for what we're doing, and then spend some time looking at how we have evaluated this. And again, I want to stress we've actually managed to validate this with over-the-air transmissions of spoofed signals and managed to detect them and get rid of them. So first, to use our methods, the following needs to be fulfilled. So we're assuming that the spoofer is using a single antenna in this way here, and that we have two different receivers, and they should be then not co-located. And we assume that they receive the same signals, both of them, so that we can actually compute things with them. We also assume that the receivers are time synchronized, so we can make exact computations of the same signal in the two receivers. We have simplified the problem by not considering multipath effects. So that's something for future work. And as I said, we need to track both the authentic and the spoofed signal at the same time to be able to follow the procedure that we're using. Okay. So to be able to mitigate spoofing, you need to detect what signals are spoofed. And we do that with a hypothesis test. And the two hypotheses that we put up is that all the signals that we're considering at a single time are spoofed. And the alternative is that at least one of them is not spoofed. So we need to determine between those. I would actually prefer to have a null hypothesis that would be that I have all the correct signals, but unfortunately we cannot really construct that kind of test. So we have to deal with this, which means that we need to detect what signals are spoofed and then the back way sort of get rid of those and then have only the authentic ones left. We do this by double differences of both the pseudorange and carrier phase. There are similar methods. And this is not really something that's new. People have done that previously in literature. What's new here, though, is that we actually combine these in a good way so that we can remove all the spoofed signal and just keep the authentic signals, and that way get a proper position estimate. So I'll start with a simple run-through of the signal model. You don't need to follow this, have all the details with you here. I'm just gonna want you to have an idea about what we're dealing with. So for the pseudorange case, we have, for the authentic case, a pseudorange that's based on the distance between the satellite and the receiver. We have a component that adds to an error due to clock drift in the receiver. We have some effects from the signal propagating through the atmosphere down to the Earth, and we have some measurement error. That is compared with the case when we have a spoofed signal, when we have a design distance to the satellite that the spoofer is using. We have some propagation delay from the spoofer to the antenna that's receiving the signal, some clock drifts and some errors. For the carrier phase, we have a similar setup with roughly the same contributions, but with additional complication of us not really knowing what wavelength or what phase we are in what period we are. So we have a wavelength that we need to deal with that we're not fully aware of. So we get a component that needs to be dealt with. Okay, so based on that, we construct differences between different PRNs in the different receivers. That gives us a way to remove all those errors that are fairly similar for all the satellites. And we just get a difference in distance and some noise. And similar for the carrier phase. Then we look at double differences. So the difference between these differences between different receivers. And the idea is that these differences will look different between the different receivers due to the different signal paths from the satellite down to the receiver. But that is not the case when you get the signal from the spoofer, because the spoofer has the same distance for all the signals to the receiver, because it's just using one single antenna, as we assumed. So that is what we have. And then you can analyze and see what kind of behavior this should have in terms of the two different cases. But let's just have a look at what things actually look like in real life to get started here. So you can do this more intricate theoretical analysis of the problem, and we have done that in a paper. So if you are interested in the details, have a look. But what you get is something like these two figures illustrate. So for the pseudorange case, if you have a spoofed signal, you will basically get a 0 measurement in the double differences, because everything cancels out based on the single antenna assumption. Whereas for the pseudorange case of the authentic signal, we get a offsetted signal that is also having an inclination, or could have an inclination. So we have a clear difference in the behavior of the authentic and the spoofed signal. That can be expressed in this way. So under the assumption that we have only spoofed signals in our differences, then we only have noise basically that measure. Whereas if we measure something that has an authentic signal in it, we will have a linear behavior over time. So something like this. And we have noise here. We assume them to be fairly similar given the background. The situation for the carrier phase is roughly the same. However, we still have to care about this unknown wavelength that we have, fixed number of wavelengths. So there is an offset here, usually from 0 for all the signals, and then we have the same behavior of actually having a linear behavior. That gives us this kind of formulation here, where in the case of spoofed signals, we have a constant term and then noise, whereas we have a linear behavior over time for the alternative hypothesis. And that is what we're actually going to use to find the spoofed signals. It could be noticed here that the noise levels here are not that easy to find, so you can't really look them up in the table. So we'll see what we can do about that. So what we're now doing is we're picking observations of different PRNs from the satellites in 2 different receivers, and then we do the double differences. And we do that for all the receivers that we have. We pick one reference receiver, and then we make double differences between that and all the other receivers. And then we collect data over a window of time, because the more data we see, the more information do we have to use to actually find the spoofed signals. So the stronger you're able to make stronger assumptions if you have more data to deal with. You can put it like this in this matrix, because it makes it easy to see that we have the window and we have different receivers. But if we vectorize this, so basically stack these on top of each other, we can see that the measurements that we're expecting to get follows a linear model, a linear regression like this under H0, and like this under the alternate hypothesis. They are the same with the difference of this theta. So in the case of the pseudorange, for example, this will be 0, because we only have noise in that case, and this would be a constant and a inclination in the case of the alternate hypothesis. Whereas for the case where we're looking at the carrier phase, we have a constant in this part here, and then we have a constant and the inclination in this other part. And the nice thing with having it on this form is that this is a standard form where we can look up test statistics for determining which of these hypotheses are the proper ones. Since these are not simple hypotheses, we have an uncertainty in the values of theta. We need to use a generalized likelihood ratio test, but that's something that we can look up. And there are forms for that are independent on the noise levels here, because you can estimate them at the same time, or you can actually assume that you have the noise levels and then construct a test around that. But we'll see that it actually turns out it's actually better, even though we have an idea about the noise levels, to try to estimate them while we're doing the test, because there's so much going on in the signal over time that it seems to change much enough so that it's difficult to actually use a set noise level. Okay, so we now have a way to determine what is spoofed. We can do that for single pairs. but we don't have a mitigation yet. So we have these decisions that can, well, they can reject the null hypothesis or not for the specific pairs. And these single signals, they appear in several different pairs, so they are not always in the null hypothesis. They are sometimes indicating the alternative hypothesis, and sometimes the null hypothesis. So what we are going to present here now is a method to actually combine these decisions to make a decision about if a certain signal at a certain receiver is something that's to be considered spoofed or not, and then perform the mitigation by simply removing the signals that we are considering to be spoofed. We could point out here that since we're actually having both a spoofed signal and a authentic signal tracked, we can from the start actually know that we are spoofed because we won't have two different authentic signals. So it's kind of an expensive method to just detect that we are spoofed, but that's not the purpose here. We're actually going to mitigate the error by removing the spoofed signal and keeping the authentic ones. Okay, so the algorithm is as follows. So for each satellite, we compute all the possible pseudorange or carrier phase signal differences for each receiver pair I and j, and then we do the double differences. That means that we get a lot of different signal differences. So all the combinations of signals. So if you have a lot of signals, we'll actually have quite a few of these to deal with. But it's not that bad. We're not having a complete explosion in cases that we need to deal with. So for each combination of two satellites that we have, we compute all the possible double differences, and then we apply this generalized likelihood ratio test for each of these double differences. And each of these tests gives us an indication if the certain combination that we are looking at right now actually can reject the null hypothesis. And we can say that, okay, there should be at least one authentic signal in here or not. And then we count how many times we cannot reject the null hypothesis for each of these signals. Then we choose to remove the signals or measurements that are indicated to be spoofed at least k-1 times. And k in this case is a threshold that we choose based on how many signals we think that we will have. And the criterion here is determined by the assumption that the spoofing system transmits k signals at least. Then we should be able to find k-1 other signals that are also spoofed. So if you get all those k-1 spoofed signals, then this is most likely a spoofed signal. So we do that, and then we remove the ones that are then meeting this criteria. Then we look at the remaining signals that we have. So it's not necessarily the case that we always remove all the spoofed signals. It might be that it's difficult to actually reject or not reject the null hypothesis. So if we actually end up in a case where we have several signals from the same satellite left in our solution, we just skip all of them because we don't know which one we should trust. And then based on the remaining signals that should then hopefully be only authentic, we compute the solution for the PBT. And then we have a unspoofed signal, hopefully. Okay, so this is the theoretical background and idea of the mitigation method. So let's now see what we find out when we do this in evaluations. So let me first give you the outline of the prototype that Niklas, as a master's thesis student, produced. It's this pipeline here. We have a software-defined radio to start with that records the signal, comes in on a RF signal there. Then we have a modified GNSS SDR tracker. So we have modified this to track all the signals that are available, both the spoofed and authentic signal. And in normal GNSS receiver, you would only track one of these. You would consider to know which one is the authentic one, and then you would track that. And then we compute all the things that I just discussed in a MATLAB script, so it's not online in that sense. We remove the the signals that we believe to be spoofed, and then we forward this to RTK-lib that would then compute our PVT solution. So that would be our new GNSS receiver. And the first and the last step are then unmodified, whereas we have introduced changes in the middle steps here. So in acquiring the signals and also how we pass on the right ones to the RTK library. Okay. So the first thing we did was to perform a simulation study. It's based on simulated GNSS data, actually GPS on the CNA on the L1 band with a Spirent GSS 9000 simulator like this here. We simulated 20 minutes of data from the summer of 2012 from a position at 59 degrees north and 17 degrees east. So it's slightly out of Stockholm, even numbers to be easy to deal with. We have a Meaconing situation. As you can see here, we have a Meaconer repeating the signal, and we have a number of different receiver positions. And what we're actually looking at determining is how important the separation of the different receivers are for end results, if there are any difference in the geometry of how the receivers are placed, how long observation windows we need to be able to get good results. We want to compare the solution based on pseudorange and carrier phase. And we also want to see if it makes any difference in having more than 2 receivers. 2 is the minimum, of course. I'll present some of the results here. If you want to have all the details, I'd refer you to the paper, which has a bit more details. But I want to give you the flavor of what kind of results we get here. Let's see. Okay, so that's the setup. So we start by looking at simulation results from 2 different receivers. And we are measuring the success in this case based on how many of the authentic signals that we managed to dig out of the spoofed situation. And I can say then that let's see, we have the number of received signals, authentic ones that we have picked out here, and we have the length of the window that we're using on this axis here, pseudorange and carrier phase. We have in all our experiments basically no authentic signals that were actually removed, and that's good. There are some cases for the really short observation windows where it happens sporadically, but in general we don't have any problems with that. We can see here based on scenario 1 and 2 that are both separated by 100 meters, but with the receivers either in the northwest southeast direction or the northeast southwest direction here, that there is actually a difference in the geometry of the problem. So that depends on how we happen to have the satellites aligned in the sky, how well we can do things. It's a bit of a difference. It's not huge, but still. We see that if we get above, say, 5 meters, the pseudorange method works fairly well. We can get a good result. And we can efficiently mitigate spoofing at much stronger levels of spoofing than regular receivers do. You can also see that with carrier phase, we have even a better situation with faster removal and authentication of signals. But at the same time, we have a stronger sensitivity to timing issues. So if you have a problem with actually getting the right timing between 2 different receivers, if you cannot wire them together, for example, the carrier phase is more sensitive to the situation. Another thing that should be mentioned is that for the pseudorange case, it was possible to choose the authentication level and the threshold in the GLR test based on theory. Basically, we can pick the values as they would come there. This does not work for the carrier phase. So what we have done here is actually made specific experiments to validate and set the level for the what should be the thresholds for the test to reject the null hypothesis. This is probably due to a bit too many approximations in the formulation of the double differences and the kind of statistics they will have. But all in all, quite positive, more or less, unless you have too short distance in between the receivers. So that's positive. In a second experiment, we have looked at results from multiple receivers. So we have a set of 4 receivers, 3 receivers, 2 receivers, and so on, and we compare them. And we see that it's actually beneficial to have more receivers, as would be expected. We have more data to work with. And the benefit of that is then we can have a shorter separation between the different receivers and still get a good spoofing mitigation. Another way we can utilize this would be to shorten the observation window and be quicker at actually identifying the authentic signals from the spoofed signals. And that works well. Next, we set out to actually see how this works in real life. And that's something that I'm quite proud of that we were able to do. So this test took place in Vidsel. It's a testing range in northern Sweden in the fall of 2019. Again, we were working with GPS signals on the CA on the L1 band. And we had only tested, in this case, mitigation based on the pseudorange. We had an attack that was constructed as a replay attack. So we had a receiver like 900 meters away from the shortest point of the receivers here that replayed its position and aimed that signal towards the receivers here. That gives us a roughly 900 meter position shift in the estimate that we should see. We test this with 3 receivers. That gives us 15 and 50 meters separation between the receivers to see how well the distance between the receivers work out. And we ramped up the jamming and the spoofing signal like this, and then ramped it down. And you can see here the reddish curve here is actually estimated in the receiver as the jamming to signal, jamming to noise level. So this is the setting. We get a saturation here, for example. That could be good to notice. The steps here that we have are 3 decibel, and they happen every 30 seconds. To be able to do our mitigation, of course, we need to have both the jamming, the spoofing signal and the authentic signal visible in the correlation graph. So it's a sort of a window here and here that works for this. So the first thing that we did that was to simply use a normal receiver, unmodified GNSS SDR receiver, and see how well it works. And what we hope to see here, and that we see, is that the receiver is spoofed and that we get this roughly 900 meter offset. That shows us that we actually have performed a proper spoofing. And we see here, so we have the spoofing level and we have the error in the estimated position. And we see that actually the receiver managed to follow the authentic signal quite high here. So around here, it actually loses the authentic signal completely. So once it has acquired the authentic signal, it will follow it quite nicely, even though the spoofing signal is more and more present until it cannot see the authentic receiver at all, or the authentic signal at all. The same thing happens when we start to take down the level of the spoofing. The the receiver follows the spoof signals all the way down to the end of the experiment here. You start to lose the spoof signal here, but it basically follows the spoof signal all the way down here without finding the authentic signal, because it follows the one that it has already. So it means that it's not so interesting to look at the signal here at the upper ramp and see what we can do, because the real receiver does a good job anyhow. But we're going to look at this region here and see, can we, with the mitigation method that we proposed, be able to find the true position earlier than here? And yes. So these are the results from the receiver A and B. You see here the result of the normal receiver without any spoofing mitigation. And we see the spoofing level, and we see the error in the estimate that we get with our method compared to the normal one. And we see that quite early we actually managed to detect that they're spoofed, and we managed to remove the spoofed signals and go for the authentic signals, basically at the same time as we managed to find the two correlation peaks in the diagram. So quite quickly, once we actually find the signals, we can do this. And the same thing happens on the receiver B. It's roughly the same result. This is a bit narrower than this, but I mean, the result is roughly the same. And for this, we use 5 peer-ends from the different satellites. And yes, I would call this a successful experiment, as we managed to find the correct position quite quickly. Okay, so that summarized the results. So I just like to give you some closing remarks before moving on. Some practical considerations. There might be problems if the receivers do not track the same set of satellites or the same satellite signals. We require that all the receivers that we have both an authentic and a spoofed signal of the same at the same time. If that is not the case, we need to do something else. And with some extra logic, you can start to actually sort out the subset of signals that can be removed or authenticated for all the receivers, and then pick pairs of receivers to remove more of them until you actually get a good result. It's also not always the case that you can remove the spoofing signal completely. In that case, you can use other methods to actually remove the spoofed signals. Receiver autonomous integrity monitoring, for example, is one method used in receivers already, so you can use that and hope for the best. We're not dealing with multipath or overlapping correlation peaks. So multipath does not behave as a spoofed signal, so you're not going to remove it with the methods that we're presenting here. So you'll have to use a normal multipath removing method to deal with that. And we cannot really help if we have overlapping correlation peaks, so that we actually widen the peak and makes it difficult to find the peak. I mean, it's not going to help what we're doing here. So such problems are not really avoided. Time synchronization seems to be, I mean, it's important. And with 2 cheap receivers, you're not going to reach the about 1 millisecond pseudorange needs to be able to use these methods. But either by having these mounted on something that you can have then a cable synchronizing the 2 units for receivers, or with some more expensive clocks, you can actually meet the requirements to use these methods. And that's, of course, then mostly really important if you use the carrier phase method. We have looked at this for stationary receivers. I mean, it's not really a huge difference if we consider mobile applications where the receivers are moving, but in that case, especially in urban areas, for example, it might be difficult to find matching pairs of signals, because there might be different signals that get through depending on the geometry of the problem and what you have around yourself, urban canyons and so on. So that's something that you have to consider when doing this. Finally, when should these mitigation algorithms be run? Well, you can actually run them all the time, we hope, and think that we can actually get them in real time, but you can also detect that something is wrong and then try to start to run them and do the mitigation there. It depends a bit on your budget in terms of energy and time, and what else you want to do with the processor. Okay, so let me conclude this talk. We have proposed a GNSS spoofing mitigation algorithm based on pseudorange or carrier phase double differences. The method works by identifying what signals are spoofed and remove them from the set of signals used for the PVT estimation. We have shown that for a separation of 5 meters, it's possible to do this with pseudorange measurements, and you could probably get even better performance if you use carrier phase, but with a caveat there that you need to be more picky with the time synchronization between the different receivers that you're using. Of course, the more separation between the receivers and the longer integration time that you can allow yourself to use, the better it is for the result. And we have verified the result both in simulation and in open sky experiments, where we sent out the spoof signal over the air and managed to still get the spoofing mitigation going. Thank you very much.
Thank you, Gustav. If you have any questions for our presenter, you can click on the Q&A button and enter those now. Okay, well, there are no questions right now. Oh, here we have one. Let's see, let me go ahead and read this from Marco Spanghero. He says, could you explain more how the system could be used in case on a mobile receiver? Also, how do you maintain synchronization between receivers in the test?
So 2 questions. Well, it's the key when you have mobile receivers is to actually know where the receivers are, so you can see how they're positioned and then do the same thing. So it's not a big issue with mobility unless you have problems with acquiring the same signals basically to compare. That can, I mean, if you're in a situation where you actually get the same signals, it's not a big issue. Otherwise, you're going to have issues to deal with. You could also, and that's something that we're actually looking forward to or into, is that if you have some inertial navigation unit, for example, in your receiver, you could use that to get the receiver separation if you're actually moving. And then you can see if the signals that you're receiving are actually matching the motion that you're expecting to get. So that's good. So to maintain the synchronization, so in the simulation, it's what's not so difficult. We actually use the time from the receiver. So it estimated the time in the receivers based on the signals and managed to use that. Now I must say I think we did the same thing in the real experiment. At least we didn't have cable between the receivers, but I'll have to get back to you on that specific detail there. But I think we actually used the GNSS signal to compute the time there as well. Is that an answer to the question?
Great, thank you for addressing that. We have another, yep, Marco says, thank you and excellent work.
Thank you.
We have an additional question. It says, what are the scalability issues, receiver deployment or automated recording of integration time, et cetera, for field applications?
Ooh, I mean, one of the scaling things here would be to actually be able to track enough different signals in the receivers. I mean, there are quite a lot of slots today to track signals based on GLONASS and GPS and whatever. You could sort of divert those to actually track a spoofed and the authentic signal. Another scaling issue would be if you have a lot of different receivers, because you get a lot of different combinations of signals to compare. So this matrix that I had with all differences in the window, and also based on all the receivers that I had. I mean, that grows. So that would be something that you would have to deal with. But at the same time, if you have more receivers, you could shorten the window because you get more decisive decisions from the GLR test with shorter windows. You can shorten that. I guess those are the scaling issues that I think of on the top of my head here. So I would probably, that would probably be the most that I would care about or be worried about. But it would be interesting to see this in a larger scale experiment to see how well it performs.
Okay, and just a follow-on question to that, what about the data volume?
Haven't really actually considered that. You don't need to send around that much data, so I don't think it should be a big issue actually. You're detecting your peaks, and then you're fine with that. You don't have to save this for future or send it to your neighbors, so that shouldn't be a big issue.
Okay, great. Okay, thank you. Do you have an email address where someone could contact you if they have additional questions?
Yes, sure. It's gustav.hendeby@liu.se. I guess you can have it and send it out maybe after the seminar.
Absolutely. Yeah, we will do that. Great. Well, thank you so much. We appreciate your time, Dr. Hendeby, and for sharing your research with us today.
Thank you for having me.
Thank you. Good evening.
Good evening.